All right, good afternoon, everyone. I've got a few notes up on the screen for just a minute, just to remind us of some due dates and everything. So please, I did say the review was going to be available by the 8th. I have already got it up there. The one thing I want to mention is I may have accidentally said last time I was going to email it. I'm putting all the reviews in Canvas. So that review is available in Canvas. You should see a tab for reviews. It's the same place that test one was sitting. But the test itself, just like test one, will go in my math lab. And I said that I will make that available from midnight, Monday the 13th until Friday the 17th. Please remember that you get 2 attempts and I'm going to take the best one. Not really doing any partial credit necessarily. And yeah, that aside, your chapter 2 homework is going to be due Thursday the 16th. So I'm just making that due the day before the test to encourage you to have all of your homework done ahead of time because it's going to help you study. All right, so we're going to pick up where we left off last time in 2.7, dealing with these inverse functions. In the previous section, we had talked about the composition of functions, which we called the chicken cordon bleu of math, where we're taking one function and stuffing inside of another. And then we related it to a function or two functions being inverses of each other if you do the composition one way and you get x. Then you do the composition another way and you also get x. So you have to have the same answer and that answer has to be x. And we gave a little bit of reasoning as to why that was last time. And then we talked about functions having to be one-to-one in order for them to be invertible. And then we gave you the algorithm for finding an inverse function when you're only given one function and you know that it's one-to-one. And I had said that this is a much more common scenario moving forward. It's not very often that we're just going to be given an f and g and asked, are these inverses of each other? It's usually more common that we're given a function and interested in finding what its inverse is for one reason or another. So again, that 4-step process was to rewrite the function notation into y equals, swap the x's and y's, which is the entire concept of inverse functions, that the x's and y's, whether they're coordinates or variables, are being swapped. Then you take that new equation, solve it for y, and change y to that f inverse notation. And I know it's typed a little funny right there. So just as a reminder, it's really supposed to look like this. That's our inverse function notation. And we did example 2a last time. So we're going to pick back up with 2b. Get our whiteboard. All right. So example 2. We're going to find f inverse of x given that f of x is 1-to-1, which means it is invertible. B, so we got f of x is equal to x cubed plus 7. So this function's a little more interesting than a, which, by the way, a was f of x equals 2x plus 5. And we had some nice easy algebra to solve for after we swapped everything. So this one's a little more interesting because, well, it's got a cube in it instead of it just being a linear term. Does that make the algebra any more complicated? Arguably, but not necessarily, as long as you remember all your different ways of simplifying things. So we said the first step was to write the f of x as y. So y equals x cubed plus 7. Then the second step was to swap the x and the y. And I'm going to use a different color to illustrate the swap. So the y is becoming an x here. And then this x is going to become a y. Everything else is going to stay in the exact same place. We're only swapping x's and y's. And there's not necessarily just a single x. There could be multiple x's, as we'll see in a later example. Spoiler alert. But now what we have to do is take this equation and solve it for y. So for step 3, that's where we're solving this for y. Well, it's not going to be just one step. It's going to be a couple steps. And let me rewrite the equation in a single color. All right, so we're trying to solve for y. So the first thing we'll have to do is move that 7. So we'll subtract 7 on both sides. And that'll give us x minus 7 is equal to y cubed. And then if we have y cubed equal to something, the opposite of a cube is the cube root, excuse me, there we go, x minus 7. So we take the cube root of both sides. Now, if that was a square, we'd have to take the plus or minus square root of both sides, as we've discussed in class. But we're just taking regular old cube roots. No plus or minus needed because they don't have that loss of sign generality. So on the right-hand side, the cube roots and the cubes will cancel. So that just says y equals. On the left-hand side, nothing simplifies, and that's perfectly fine. So we get the cube root of x minus 7. The fourth and final step is instead of writing y, we have to write that as f inverse of x. So we have the cube root of x minus 7 is equal to f inverse of x. Remember, that does not count as a -1 for an exponent. It has nothing to do with a reciprocal. It just relates to a reciprocal because that's the opposite of a multiplication. And inverse is the opposite of a regular function. And that's our answer. If you want to make the inverse be on the left side, it doesn't really matter. But I know a lot of people like to see the function on the left, so I will do that. So f inverse of x is the cube root of x minus 7. So once again, we had the function, we wrote f of x as y, we swapped the x's and y's, we solve for y, and this could be any algebra technique that we have done together. And then once we have y equals, we have to make sure that we change our notation. Remember, if this was paper pencil, if you just left that as y equals, that would not be good enough for me and a lot of teachers because you're not representing the inverse function. How do I know that you know it's the inverse function, in other words? All right, so C, let's do an interesting one. You might think that B was interesting, but C is more interesting, and we'll see why in the answer. So f of x equals 1 over x. This is the base reciprocal function. This is known as the reciprocal function. I'm just going to abbreviate. It's the reciprocal function because it says whatever number you had, take 1 and divide by that number. In other words, flip it upside down. It's also the most basic rational function. So this is the most basic rational function, and it's something that we will learn how to graph in a later chapter. But for now, we're just doing its inverse. So first step, write f of x as y. That's y equals 1 over x. Second step, we're going to swap the x's and the y's. So wherever you saw y, you now write x. Wherever you saw an x, we're now going to write a y. So again, the blue is showing you what has changed. All y's turn into x's, all x's turn into y's. And then we're going to take this equation and we solve it for y. And let me just rewrite it with the same color. Now the thing that we want to solve for is in the bottom of a fraction, and it's the only factor in the bottom of the fraction. The way we get things out of denominators is we multiply by that, in the same way that if you had 3 times x, you would divide both sides by 3. This is like having the 3 in the bottom, so we multiply both sides by it. And having the variable we want solved for in the bottom is not ideal. So that's why we are going to multiply both sides by y. In case you need to see this step, you can also say, oh, that's an LCD of y, and now I'm eliminating all the fractions. It's the same idea. So the y's on the right-hand side are now gone. The left-hand side, it says y times x. I'm going to reorder them. We just tend to like things in alphabetical order inside of a term. So we get xy equals 1. Now, this at least is not in a fractional format, so it's prettier, but it's still not solved. Again, we're supposed to be solving for that y right there. It's currently being multiplied by x, so we got to get rid of that. To get rid of it, we will divide both sides by x. Some people might say, well, why didn't you just take the x and write it over 1 initially and cross multiply? Guess what? That would have worked too. Per usual, in math, there tends to be more than one way to get a job done. So our x's cancel on the left, so we get just y equals 1 over x. So this was all step 3. And then step 4, we're supposed to change the notation. So instead of writing y, we write this f inverse of x. So f inverse of x is equal to 1 over x. And that is the answer. And this is normally where I'd ask the class, why is this answer interesting? Well, look at what the original function was. The original function was 1 over x, and the inverse is 1 over x. They're the same thing. F of x for this particular problem is the same thing as its inverse. And that might seem weird at first, but it is possible. It's very rare. There are not a lot of functions where if you were to invert them, you get themselves, but they do exist. These are basically your zeros and your ones. 0 under addition is its own inverse, because under addition, 1 and -1 would be inverses, because when you add them, they cancel, you get 0. So 0 is its own inverse under addition. 1 is its own inverse under multiplication, because if you multiply 1 by itself, you get 1. You get the identity under multiplication. So this is a pretty rare function, but there are more of these that exist, but I wanted to make sure we at least saw one of them because it's quite interesting. Don't expect this to happen a lot, but it can happen sometimes. Let's do another. We're going to do several of these because it's something we definitely want to have practice with. And this will be a similar function starting out, but with some extra characteristics. So let's go f of x equals 3 over x plus 5. So this is still a rational function because it's got a variable and a denominator. It's a fractional function, in other words. But it's not as simple as the last one because we have, well, 3 and 5 in here and the 5 is separated. But that doesn't matter. We're still going to go through the 4-step process. So first, rewrite the f of x as y. So that's y equals 3 over x plus 5. Then the second step, it's a really ugly looking x. This is where we swap the x and the y. So the y becomes an x, and that x in the bottom becomes a y. And then we take this and we solve it for y. Let me rewrite it again all in the same color to avoid confusion. Now, again, the thing that we want to solve for is in the bottom. We don't like that. We don't like having equations with fractions. We really like to clear out all the fractions 99% of the time, especially if the thing we want to solve for is in the bottom. So we're going to do the same technique as last time. We want to identify our LCD, the only denominator we see, which is y, and that's what we're going to multiply every single piece by. Now, if it's a fraction, it only goes in the top. So we take the x times a y on the left, the 3 times a y, and the 5 times a y. Doesn't matter if the y's are going in front or after the pieces. The reason we've done that is because in the first term after the equals, we will get rid of the only fraction we see. That is beneficial. The left side, we have that y times x, which is just better to write it as xy, then equals. Now, this term that was a fraction, the only thing that's left over is the 3. And then we have the 5 times y at the end. Now, remember, we're supposed to be solving this for y. This is different. This is more interesting than the last 3 problems because there is more than one y up here. There's 2 y's. We have a y here, and we have a y here. And they are on opposite sides of the equation. This is something we were dealing with back in chapter 1 when we had those literal equations or formulas, depending on what you like to call them. And this was one of the more advanced types of problems where we said, all right, the variable that you're trying to solve for, you need to move all of the terms that have that to one side. And it doesn't matter which side, but you have to move them all to one side. And then any term that does not have that variable needs to go to the other side. So there's a y on the left, there's a y on the right. There's also this 3 that does not have a y. Well, there aren't any non-y terms on the left, so we should probably just leave the 3 on the right. That would be the easiest thing. Again, not the only way to do it, but the easiest. So we need to focus on moving the 5y to make this a shorter problem. So let us subtract 5y on both sides. Now I'm going to squeeze it kind of under this xy, but arguably it shouldn't be under it because those are not like terms. Xy minus 5y, there's absolutely no way we can combine them. So we just write exactly what it says. Xy minus 5y equals, the 5y's on the right side will cancel, and we get just our 3. So we're a little closer. The variable we're supposed to solve for is now on the same side of the equation, and then everything else is on the other side. Now, if these were like terms, we would have combined them. If this said 8y minus 5y, we'd have 3y, and it'd be pretty easy. But again, there's a y here and a y here, and they're not like terms. So the alternative is to take a GCF out, and that GCF should generally be the variable you're solving for. So let me move up here. So again, what we had was xy minus 5y equals 3. We're going to take the y out, so we open a parentheses. If you take y away from the first term, you're only left with the x. Then minus, if you take y away from the second term, you're only left with the 5. And then the 3 is still on the right-hand side. Now, this problem right here is very similar to having something like 5y equals, 40. You'd have to divide by the multiplier of the y. But this isn't just a number times y, it's this parentheses times the y. So what we have to do is divide both sides by that entire parentheses. We divide by the thing we're not solving for, because that will get rid of those and leave us with just our y. Remember, we're always trying to think about what our goal is. We're not just doing random steps. These are goal-oriented steps. And on the right-hand side, we've got 3 over x minus 5. Nothing simplifies there. And some students would then box this up and ship it out, but this would not get you full credit because we did not signify that we know this is an inverse function. We have to use the notation. F inverse of x is equal to 3 over x minus 5. This is the most challenging type of problem for these inverse functions that I would give you on homework or test, in my opinion. Of course, challenge is subjective. But the reason I find it challenging is because you've got to know how to clear out your fractions. We saw that in another problem, but then there was more. Now this time we had multiples of the variable we wanted to solve for, so we had to remember that technique from before where we move all those terms to one side and everything else to the other side, take a GCF out, and then divide by the last bit. So the algebra is just a little more intensive here, but it is the same set of principles. All right. So let's do another one of these, and we're going to change it up a little bit. E. F of x equals x squared plus 11. And then I'm going to say for x is bigger than or equal to 0. This is known as a restriction. So what I want to do before I actually get into this problem is I want to show you why this restriction is important. Without this restriction, we can't actually do this problem. We can't get an answer. We can try, but we're not going to get an answer. And unfortunately, a lot of people will usually mess this up because they forget a super important element that I've reminded us probably 500 times never to forget. So before we move on, let me do in a different color. Let's say the restriction was not in place. So we just had f of x equals x squared plus 11. I'm going to go through this really, really quickly. You write your f of x as y. Then you swap. So that's x squared. I'm sorry, not x squared. X equals y squared plus 11. Remember, only the letters are changing, not their components. And then we solve for y. So we'd have to move the 11 over, which would give us x minus 11 equals y squared. Now, this says y squared equals. I mentioned this earlier today. The opposite of a square is a square root, but when these are even, you have to throw in that plus or minus. So this is where we have x minus 11 equals y squared. I'll show this one in color. So we take the plus or minus square root of both sides, but the plus or minus only goes on the non-y side. And it is this right here that causes the issue. So now what this says is we have plus or minus, that was weird. The square root of x minus 11 is equal to y. This plus or minus is a problem. And let me say it's an issue. It's not a problem as in a math problem. It's a complication. It's an issue. Just plug in an x value of, say, I want to make this a nice even number. Let's say we used x equals 12. That tells us that y is equal to plus or minus the square root of 12 minus 11, which is plus or minus the square root of 1, which is plus or minus 1. So that is one input leading to two outputs, which means it's not a function. So the inverse is not a function. This was supposed to be the inverse function, but it's not a function because of the plus or minus. This was an issue we talked about, I don't know, maybe a week before spring break, something like that. So, okay, does that mean that we can't invert this function? No, all we have to do is restrict the domain. Why are we restricting the domain of the original function? Because we can't have this issue in the range of the inverse. Remember that the domain of f of x is the range of f inverse of x, because your inputs and outputs, they're all swapping. The input of a function is the output of an inverse. The output of a function is the input of an inverse. So the domain of one is the range of the other and vice versa. So we need to restrict the domain of f of x to be positive, then no negative outputs in f inverse exist, i.e., no plus or minus needed. Let's not update Windows 10 right now, thank you. Okay. So again, the input of one is the output of the other. So by restricting the domain of the original function, there are no negative outputs of the inverse function. I'm sorry, there's no negative let me say that one more time. I got focused on what my computer was doing. By restricting the domain to be all positive numbers, that tells us the range of the inverse has to be all positives. So there's no more plus or minus. The negative can't even exist. So that is why we have this condition. So I'm going to do literally the same algebra that's in blue, except for the last step with the restriction. So going back to E, f of x equals x squared plus 11, where the x is going to be positive. So we have that as y equals x squared plus 11. We'll swap them and write it as x equals y squared plus 11. We'll subtract 11 on both sides. We'll take the square root of both sides. Remember, there's no plus or minus by that. So we get the square root of x minus 11 is equal to y. And then we switch our notation, so that's the square root of x minus 11 is equal to f inverse of x. And again, if you just want to swap the left and the right side, you can. So again, the last time I'll say it, I promise. By restricting the domain of the function to just be positives, that means that the range of the inverse function can only be positive. So when we do the square root of both sides, there is no plus or minus because we're ignoring all negatives in the range of the inverse function. And when we swap the x's and y's, that's when domain and range is swapped. Now, what's going to be fun is we're going to come back to this example in a graphing manner very shortly. But this is a pretty common tactic in advanced math, where we have a function that isn't invertible everywhere. So instead, we just narrow our field of vision. We narrow our window to something that we can invert. And it'll be helpful to have that visual aid. So let's get into that. Share screen. So here's that same memo I had written in handwriting before. By forcing the x to be positive, the inverse function's output can't be negative, thus avoiding the plus or minus. All right, so now let's get into the graphs. Let's give this a little bit more of a visual sense. Hold on, give me 5 seconds. Sorry about that. Okay, so if we're graphing, if we want to know if a function is invertible, in other words, if an inverse exists, it has to pass the horizontal line test. And I alluded to this last class. For functions, we had the vertical line test, because if a vertical line goes through a function more than once, that means that one input is leading to 2 outputs, kind of like when we plugged in x equals 12, leading to plus and minus 1. That would fail the vertical line test because we'd have a height at +1 and a height at -1. So the horizontal line test is so because, well, with a function, we're swapping inputs and outputs. We're swapping x's and y's. So when we swap this, a vertical line becomes horizontal. So if you fail the horizontal line test of a regular function, that means you'll have let's just keep this on the positive. Here's your function right here. So the horizontal line test, you're just drawing a bunch of horizontal lines, and each one is allowed to cross once. So this has an inverse. But if your function looks like, I don't know, let's do a circle. This, you've got lines that would hit it twice, so it would not have an inverse. Because if you inverted this, these horizontal lines become vertical and it fails the vertical line test for being a function. To begin with, the circle is already not a function, which means that its inverse can't be a function because it fails the vertical line test as well. So it's a pretty easy test to use. It's something that we should have a good idea on how to use it. But let's try it out anyway. So example 3. Does an inverse exist? And we're going to do 3 of these. For A, let's do a line. Looks something like this. Label our axes. And I'm even going to put this height at a very specific number of 5, where it crosses the y-axis. So that's its y-intercept. So we're going to use the horizontal line test, and I'll switch my colors this time. Here's a horizontal line, mostly. Ignore my mediocre artistic ability. And it crosses once. Here's a horizontal line, and it crosses once. Here's a horizontal line, and it crosses once. I could do this 5 billion times, and every single one of these is just going to cross at once. So guess what? Yes, an inverse does exist. Now, I didn't demonstrate the slope, but I'm going to pretend that this is a slope of 2 with a y-intercept of 5. Guess what? Oh, that's right, we did that last class. Never mind. This is y equals 2x plus 5. That's the line that I just graphed right there, which was example 2a, which we already proved via algebra that it had an inverse because we found it. All right, B. Let's do a parabola. And let's do one that has a very specific height of 11 for its y-intercept. So that's an 11 there if you can't see that. And then we make some horizontal lines. Let's just do a bunch down here. That doesn't touch it at all. Remember, the y-axis is not the graph. This doesn't touch it at all. This doesn't touch it at all. And even if I draw it at a height of 11, if I do that perfectly, that one only touches one time. So this definitely has an inverse, right? Well, no, because you have to be able to draw that anywhere. And if you draw it any higher, once, twice, boom, that fails the horizontal line test. So, wrong color. No, there is no inverse function for this. And guess what that's the equation of? Did you guess it? It's x squared plus 11. So earlier we discussed algebraically why this didn't have an inverse, and it's because when you went to try and solve for the y after you swapped your variables, you needed that plus or minus, which fails functions. Graphically speaking, it's because it fails the horizontal line test. C, last one. Same thing, let's have a height of 11, but let me only draw the right half of this graph. So by only drawing the right half of the same graph, any horizontal line down here still touches it 0 times. The horizontal line at a height of 11 is still touching once. But now when I go to draw any horizontal line higher, that only touches once. That only touches once. This is a function. I'm sorry, this has an inverse function. It passes the horizontal line test. They were all functions. The first one has an inverse, the second does not, the third one does. Guess what this is the equation of? Y equals x squared plus 11 for x having to be bigger than or equal to 0, which was example E previously. So D graphically shows the complications that were equivalent to the plus or minus issue from the algebra. C shows us by removing the left side of that, by narrowing our field of vision, by narrowing our window, we can take a non-invertible function and make it invertible. Can you always do this? No. Can you do it a whole lot of the times? Yes, you can, in fact. So pretty easy to tell whether an inverse exists or not graphically. You just have to remember the details. You have to remember that touching twice is bad. And you have to do horizontal lines, not vertical lines. Okay, new share screen. Back to this. Last topic of 2.7, finding the inverse function given the graph. We've already talked about this. It's the exact same idea as everything for inverting a function. You swap the x's and y's. If I give you an equation, you swap the x's and y's. If I give you sets of points, you swap the x's and y's. If I give you a graph, you swap the x's and y's. But I do make a special note here. This is really cool, and I don't really suggest using this aspect because I find that a lot of people have a hard time reflecting about a diagonal line, but it does work if you practice it. And I'll even speak from personal experience. I don't always reflect these perfectly. So the graph of an inverse function should be a reflection of the original graph about the line y equals x. And the reason that this is an x right here has everything to do with what spits out when you do that double composition either way. Because that's an x. If for some reason, if functions were inverses, if their compositions were, let's say, 17x squared, so if both of those were 17x squared, that means the reflection would be about the curve y equals 17x squared. So it's because this is an x, stuffing one function inside of the other both ways, if they're inverses gives you x. That is the reason that this is the reflection. This is not something I'm going to test you on. This is just an extended concept that is nice to understand. What you have to be able to do is swap the x and y coordinates. That's what you'll be doing. All right, to the whiteboard, new page. What are we up to? Example 4, and there's no A or B, just example 4. Graph the inverse. So I'm going to give you a picture, and I'm going to describe very carefully some points, because this is going to be a piecewise defined function of line segments. So I'm going to have a point over here at -1, 0, then a point at -3, -2, and then a point at 4, 2. 1, 2, 3, 4. That's -1, -2. What am I doing? That was silly. -3, -2, -1, 1, 2, 3. I keep doing that. So again, those points, and I'll label them in red. This point over here is -3, 2. This point here is -1, 0. This point here is 4, 2. So this is a piecewise defined function because we've got this line segment between the first and second point, then a different line segment from the second and third points. These do have different slopes. It doesn't look exactly the same, but you can see if I extended the first segment, it would be up here instead. So this is f of x. Let me actually write these as a table of values. So x, f of x. Am I missing the negative? I am missing the negative on the 2. Thank you for catching that. -3, -2, -1, 0, 4, 2. Okay, good. So that first point, we're going left and down, so that's -3, -2. The second point is -1, 0. The third point is 4, 2. So this was the regular function. Let's swap all coordinates to get the inverse function. So swapping these coordinate pairs just means the x and the y, the right column is always the y value. That just means just change the numbers, flip them around. So that's now -2, -3, then 0, -1, and 2, 4. So there is the inverse set of coordinates. So we're going from -2 to +2 on the x's. And then the y's are going from -3 to +4. So -2, -3, that's left 2 up left 2 down 3. I really don't want that second coordinate to be negative, do I? Left 2 down 3. Then 0, -1 is left to right 0 down 1. And then 2, 4 is right 2 up 4. And if you connect these together, again, different line segments, that slope does change drastically. It's got like a corner there. It doesn't look as drastic this time. Make it look a little better. And again, those points were -2, -3, 0, -1, and 2, 4. So this is f inverse of x. Now I'm going to redraw both of these again, but I'm going to put them on the same graph because I mentioned that extra little thing about you can tell that they're inverses because they're a reflection about the line y equals x. But that's the answer. That's all I asked for. Someone just asked, what if you had the graph of a line y equals 5? That would fail the horizontal line test miserably because if you put that horizontal line at a height of 5, it will hit it infinitely many times. So it's not that the graph is not a function, it's that the inverse is not a function because it fails the horizontal line test. Y equals 5 is a function. X equals 5 would not be a function because that's a vertical line and fails the vertical line test miserably. Okay. All right, so last bit for this section, let's put everything on one graph and I'll do them in different colors. So let's just go -4 to +4 in each. All right, so we had -3, -2. I'll do this one in red for the regular function. That was left 3 down 2. Then we had the -1, 0. And then we had the 4, 2. So this is f of x. In blue, I'll do the inverse function. So that was just all the coordinates swapped. So -2, -3, that's left 2 down 3. Then the 0, -1, left to right 0 down 1. And then 2, 4, right 2 up 4. And then I'm going to connect these. That's kind of, let me try that again. A little better. So this was f inverse of x. And then in green, I'm going to plot the line y equals x. Well, y equals x goes to the point 0, 0, and 1, 1. And I'm going to do this as a dotted line because it's supposed to be a mirror. Oh, that was awful. So that's the line y equals x, which is our mirror. So can you see that it's a mirror image? It almost ends up looking like a DNA strand or part of one before I did the mirror. But you can see that if you reflected the red across that green line, you'd end up with the blue. But you can also see why if these were bending a lot more, if these were more complicated functions or curves, it might be a little more difficult to handle that aspect graphically. I'm not saying you can't, I'm just saying it might be more difficult. But for those that master that technique, it does give you the inverse function quicker, ultimately. So that way that you're not having to plot a whole series of points. Alrighty, so that will conclude 2.8, our inverse functions. 2.7 is done, so let's go to 2.8. And you're going to see more of that x1, y1, x2, y2 stuff in here, where these are not written in subnotation. Please forgive me on that, but all of those should be little ones, and they should be a little lower than the x's or the y's. So, and let me not put everything up here all at once. That's not fun. 2.8, distance, midpoint, and circles. You get 3 formulas in this section that you have to memorize and be able to apply. The circles, there were originally 1 or 2 problems in the homework that should not have been there. If you got to that homework super, super early, I want to say it was like problem 13 and 12, the last ones. Those I'm not counting as being graded because they're a little above and beyond what I expect of you from this course. And it's interesting because the last version of the textbook we used we didn't cover that stuff. So I don't know why someone put that there, but it doesn't matter. We're going to keep this easier. So formulas, putting numbers into a formula, that's pretty much it for this. So let me use my pen. So this should really be x little 1 comma y little 1 and x little 2 comma y little 2. So those are our 2 points. The distance between any 2 points is found by this formula. D equals the square root. It's a big square root. We have a parentheses inside of that square root. And in that we go x2 minus x1 squared, then plus, in parentheses, y2 minus y1 squared. Got to memorize this. There are a lot of things that you can mess up in this formula and still get the right answer. There's also a lot of things you can mess up in this formula and get a very wrong answer. Most commonly, people get the minuses and pluses mixed up. They'll just do all minuses or all pluses. What this is here is the difference of the x's, the change, and the difference of the y's. We've seen change before with the slope formula. Slope was y2 minus y1 over x2 minus x1, where we called each of those subtractions a change. So this is the change in x squared, and this is the change in y squared, and then you add those and take the square root of them. If you've ever heard of the Pythagorean Theorem, this is exactly what it relates to. If you have 0.1 here and 0.2 here, this distance is the change in x. This distance is the change in y. And then this, if you called it c, would make the change squared plus the change squared equal to c squared. So if I just call that a, and I call this b, and I call this c, a squared plus b squared equals c squared, and then you just take the square root of both sides. Mr. Beckner, why not a plus or minus? Because this is geometry, there are no negative links in geometry. So again, the distance equation is literally just the Pythagorean theorem between 2 points, if you make a little right triangle out of it. Okay, so let's try this out. So now we are in 2.8. Let's go back to black. Example 1. Find d, which means the distance between the 2 points. For problem A, we'll go 2, -5 and -3, 6. If you want to label things, you can. From left to right, the 2 is the x1, the -5 is the y1, the -3 is the x2, and the 6 is the y2. And then we just plug all of that into the formula that we saw before. It's a big old square root, big square root. We got 2 parentheses being squared added to each other, where each of those parentheses is a change. It doesn't matter the order that you do these as long as you take the differences of the x's and the difference of the y's. You can do the y's before the x's. That won't affect the final answer. You can actually screw up the order of the 1s and 2s. Now with slope, it just meant you had to be consistent. 1 minus 2 in the top, 1 minus 2 in the bottom, or vice versa. With this formula, you can do 1 minus 2 in one of them and 2 minus 1 in the other, because you're going to end up squaring them. So all the negatives that you get from doing them backwards are irrelevant. They'll go away. It's a loss of sign. But I do like to apply the formulas in the correct given order. I don't want to say correct, just the given order. So I'm going to do x2 minus x1. x2 is -3, minus x1 is +2. Again, x2 minus x1. Then plus parentheses squared, and that's a difference, with y2 minus y1. 6 minus -5. Watch your double negatives. So that says our distance is the square root of -3 minus 2 is -5. Square it, plus. That's 6 plus 5. I'm going to skip writing that extra step, but that is 6 plus 5, which is 11, +11, and we're squaring it. I didn't need all that extended part of the square root, but no worries. A -5 squared is +25. 11 squared is 121. And that tells us that d is equal to the square root of 146. If you know the square root, you have to take it. If this was 144, we'd say the answer is 12. If you don't know the square root, you've got to see, well, maybe you can break this up. Can you write this as a product of 2 numbers where you know the square root of one of them? In the interest of time, I will mention that no, we don't. You might think 4 times something, but 4 is not going to go into that. There is no way to split up this 146. So that is the distance. Now, if you're curious what that is as a decimal, it's 12 point, sorry, I had to pull out my calculator. This is approximately, and I'll round to 3 places, 12.083. That is not the answer that I'm interested in. I am not interested in the approximation unless the instructions say, give an approximation. Because remember, we're still in a no calculator test in theory. So how would you be able to do that without a calculator? This is what I want. But if you can break it up and simplify it, then please do. And again, the order of the 3 and the 2 didn't really matter. If you did 2 minus -3, that'd be 2 plus 3, which is 5. Now it's different signed here, but when you square it, you'll still get 25. If you swap the -5 and the 6, -5 minus 6 is -11. -11 squared is 121. If you swap the order of the 5s and the 11s, that's relevant because you're still just adding them, and the order of addition never matters. So again, there's a lot of things you can do in an inappropriate order and still get this right. For distance, All right, B, let's do 0, 4, and -1, -2. Again, if you want to label them, x1, y1, x2, y2. So our distance, big ol' square root. Sum of squares, just like Pythagorean would have. But it's not just an a squared and b squared. These are changes. These are differences. The difference of the x's and the difference of the y's, honestly, in whatever order you like, but I'll be consistent. x2 minus x1 is -1 minus 0. So I'll put that in the first. I can put in the second if I prefer instead. Doesn't matter, but I'm being consistent. Then the next one is the difference of the y's, -2 minus 4. Simplify, so square root, -1 minus 0 is -1, but we still got to square that, so don't drop the parentheses. -2 minus 4 is -6. Again, don't drop the parentheses. So that's square root of -1 times -1 is 1. -6 times -6 is positive 36. You cannot take these square roots individually. Please don't do that. I didn't do it in the last one either. That's not how square roots work. It works that way for products and quotients, not for additions and subtractions. That's the square root of 37, which guess what? You cannot simplify. Anyone who's curious, just to have a tangible number there, that's the square root of 37, 6 point something, 6.083. Again, I'm really not interested in the rounding here, but I know that some of you like tangible numbers to be able to gauge how big this is. That's saying the distance between the 2 points is about 6. It's really close to 6. So in other words, if you plotted these 2 points perfectly, you weren't just doing this by hand, you used a ruler or something. If you then connected the 2 points, let's say you made the distance between 1 and 2 a single inch, and then from 2 to 3 a single inch, etc. If you got your ruler, if you measured the distance from the 2 points, if you did this everything entirely accurately, you would be able to measure that it's about 6.1 from the first point to the second point. All right. New share screen. Next up, next topic, the midpoint. Oops, too far. The midpoint between 2 points, and again, those are supposed to be an x1, y1, and x2, y2, like that. Now the midpoint is a point. Points have an x and a y coordinate. So this isn't just one value, it's 2. So I like to go MP for, as you may have guessed, midpoint. What this is literally is the average of the x and y coordinates. You're going to average the x coordinates, which means add them and divide by the number of them. So we're going to add the x1 and the x2. And since there's 2 values there, we divide by 2. That is the x coordinate of the midpoint. Again, it's literally just an average. Add the 2 values and divide by the number of values. The y's are going to look almost identical. y1 plus y2 divided by 2. That's an ugly 2 in the bottom. There we go. A little better. Again, these are just averages. An average means add them up, divide by the number of things. You have to average the x's and the y's separately. The x's are apples, the y's are oranges. They're different categories, inputs and outputs, not the same thing. And yes, when you plug in an apple, you get an orange. Ha ha ha. So that's our midpoint formula that you have to, no surprise, memorize. And that down there, that's an abbreviation for averages, AVGS. 10 seconds. Okay, let's try that out. Example 2, find the midpoint. the halfway point, the average point, if you will. And we'll go from 2, -5 to, let's say, -3, 6. Per usual, should you want to label, that's x1, y1, x2, y2 from left to right. If you want to call the second points the 1s and the first points the 2s, be my guest, nobody cares. So our midpoint, again, this is a coordinate pair. Some x number, then a y number, where each of these is the average of the x's and the y's. I'm not adding 2 and -5 because that's an x and a y. We're averaging the x's for the x spot. So we take the 2 plus the -3 and divide by the number of x values. That's the average of the 2 and the -3, the average of the x's. The y's, we're going to average them. That's a -5 plus a 6 divided by 2. 2 plus -3 is -1. So that's -0.5, comma. And then -5 plus 6 is +1, so that's +0.5. There's nothing else we can do there. That's the answer. So the halfway point between those 2 points is -1/2, 1/2. Now again, in application, what you can do is you could actually perfectly draw everything up, ruler, computer, whatever, plot the 2 points. If you then connected them with a line, if you measured the distance from those 2 points and then took half of it and put a dot right on the halfway point, that's exactly where it would be, at -1/2, +1/2. For B, let's do -5, 12, and 7, 20. Labeling, if you like, x1, y1, x2, y2. If it's an improper fraction, do you change to a whole number? You can only do that if it divides perfectly. I think what you may have meant to say is a mixed number, and that is up to you or what my math lab says. I'm a bigger fan of leaving things as improper fractions, but making sure to reduce as much as possible personally. No problem. Okay, so back to our B, our midpoint. Averaging the x's, that's the -5 and the 7. So -5 plus 7 all over 2, comma. Then let's average the y's, 12 and 20. So 12 plus 20 all over 2. -5 plus 7 is +2. Leave the over 2, comma. 12 plus 20 is 32. Leave the over 2. But both of these are divisible. So 2 divided by 2 is 1, so that's 1, comma. 32 divided by 2 is 16. So 1, 16 would be our answer. So again, we had some improper fractions here, but they were perfectly divisible, so they turned into whole numbers. These are not insanely crazy formulas to have to use. We've done one formula in particular that's been way crazier than that. The quadratic formula. If you can handle the quadratic formula, I expect you to be able to handle this. And my expectation is that everyone in this class ultimately handles the quadratic formula. Because as I say, it never goes away. Never, ever, ever, until you stop taking algebra-based math. All right, third and lastly, circles, which I just have the word circles written there. In fact, because of that, let's just, well, I do have the instructions, so I'll leave that. Okay. Equations of circles. The equation of a circle with radius r and center h comma k is the following. Here we go. Parentheses. X minus h, close it, square it, plus parentheses, y minus k, close it and square it, equal to r squared. And you have to memorize this, of course. Now, what you may notice is that this is similar to the distance equation. In fact, this is literally that Pythagorean theorem again, a squared plus b squared equals c squared. Now, why do they use the letters h and k instead of x1, y1, x2, y2? Because the center is not actually a point on the circle. The center is just a frame of reference. And someone a long time ago decided to use the letters h and k, so that's what we use for this. And it's not the only time we'll use the letters h and k in this course. When we talk about the vertex of a parabola, we'll use the letters h and k, and maybe one or two other things as well. But again, this is really just the distance equation, but instead of writing x2 minus x1, it's x minus h. So we're making one of these an actual variable instead of a value. Same thing here, instead of writing y2 minus y1, it's y minus k. So the h and the k are kind of like the x1, y1, but we don't call them x1 and y1 because they're not actual points on the circle. We give them a special name. And then that hypotenuse would be the r squared. So let's say we had I don't want to do it that way, actually. We got our circle. That's a terrible looking circle, and I want to make it a little bigger. Better, okay. Here's our center. And let's say we were at this random coordinate x comma y. We don't have to be at that point. We can be anywhere on this because every single one of these is a point on the circle. So this x comma y, these are variables. They're allowed to be anywhere on this. I'm just putting it there. So this distance right here, that's the change going from x to the center. Well, that's h. So that's x minus h. This vertical distance, that is y minus k. That's the difference of the y values. Y, and then this center is h comma k. That's the point there. And then if I draw a connecting hypotenuse between these, forming a right triangle, well, that's the distance from center to end. That's known as the radius. And Pythagorean theorem says a squared plus b squared equals c squared. A is the blue, b is the green, the c, the hypotenuse is the r. So that's where that equation comes from. So we're going to do two different types of examples with this. One of them, I'm going to give you the radius in the center and ask for the equation. And then I'm going to give you the equation and ask you to identify the information. So we'll go both ways on this. We'll do the regular problem and then we'll do the inverse problem. That has nothing to do with inverse functions. I just am trying to connect the dots there. Because this section really is its own entity. Everything else in chapter 2 kind of flows together. This is the odd man or woman out. All right, whiteboard. Example 3. We're going to write the equation of a circle. EQN, I'm abbreviating for equation. Given the info. And then let's also graph these. For A, let's have a radius of 4 and a center at 0, 0. So centered at the origin, the easiest case possible. So with a radius of 4, well, we know the r. With a center of 0, 0, we can identify that as the h and the k. So 0 is the h and 0 is also the k, but it's the first 0 is h, the second 0 is k. And then we just plug everything into that formula. So the formula was a parentheses squared, and it was x minus at first. Then a plus, a parentheses squared, each of these are changes, with a y minus. And then that was equal to the radius squared. But I got to plug those three numbers in. The h is what goes with the x coordinate goes with the x variable. So that's a 0, because this is a 0. Then y minus, because the y coordinate of the center is 0, this is a 0. And then equals the radius squared, which is 4 squared. Please don't forget the square. A lot of people can do that. Now, this is not always simplifiable, at least very much on the left side, but this one definitely is, because subtracting 0 does nothing. So that's just x squared plus y squared equals 4 squared, which is 16. That is the equation of a circle. And way back in the semester, when we first started, I showed you, I believe, the equation of a circle with radius 5. It was x squared plus y squared equals 25. So that format sounds familiar, so hopefully we weren't lying back then, especially since we graphed it and all that stuff. So that's the equation. But I also asked for the graph. So let's make a graph. Now the radius is not 16, the radius is 4. You got to be careful here. Some people will look at the equation and think the radius is 16 because that's 16, but the format was supposed to be r squared. So the radius is 4. So I'm going to make a red point for the center. This red point, the origin, is the center. That is not a point on the circle. The circle is going to be around it with a radius of 4. So let me go 4 to the right, 4 up, 4 left, and 4 down. Now, to draw a circle, I like to make points on what I call the cross of this. I go left, right, up, and down based on the radius to find out where we're supposed to be. It's pretty easy to tell where we're going to be for this problem because we're centered at the origin. Spoilers for the rest of the problems, that's not going to happen again. So if we start at the center and go right 4, we end up with this point. If we start at the center and go left, we'll get this point. If we start at the center and go up 4, we get this point. If we start at the center and go down 4, we get this point. Kind of looks like we're going to draw a plus sign, but that's not what we're doing. We're supposed to be drawing a circle. So connect these 4 points in a nice circular arc as best as you can. I'm doing the best I can. I really am. That's actually not much worse than what I'd get on the board. There's our circle. When you're in my math lab, when you're using the math palette, there is a circle button that you can click. So you'll click where the center is, and then you just drag in or out to make it bigger or smaller. So you need to make sure that you made a radius of 4. It's actually a lot easier in my math lab, as long as you understand how to use it. So that's A. B, let's go with a radius of a square root of 7, centered at the point 2, -5. Okay, so if the center is 2, -5, that means the h is 2 and the k is -5. With the r being a square root of 7, when we plug that in, well, something's going to happen to the square root, spoilers. That's all we need. We need the radius in the center. So the equation of a circle goes parentheses squared plus parentheses squared, just like the distance, but instead of having a square root of all that stuff, the right-hand side is going to be the radius squared. Inside of these, it's x minus and y minus. So the variable minus the fixed center, variable minus the fixed center. What's our center? 2, -5. So the 2 goes with the x, so that's x minus 2. And the -5 goes with the y. But watch this, that's negative. So you end up plugging a negative in, you're subtracting a negative, that's going to become a plus. That's going to be an important aspect to figure out, or to understand, not figure out. The radius was the square root of 7, so that is what we're squaring on the other side. This kind of looks like a J. There we go. There are 2 things we can do with this. The x minus 2 squared we can't do anything with, but we can fix that double negative to a y plus 5. squared, and the square root and square on the right cancel to just give us a 7. Now, in order to draw this, and this is not something I would normally do on a homework or test, but because this has a square root of a radius, we need to get an approximation for that. So please note that r is approximately, and I'm just going to do this to 1 decimal 2.6, about 2.5. So that's how much I'll go left, right, up, and down from wherever I plot the center, which was at 2, -5. So I got to be right 2 and down 5. I need more of a bottom heavy graph for this. So we're gonna go right 2 for the center and then down 5. 1, 2, 3, 4, 5. We'll make that a red point, red for not actually a point on the circle. That was at 2, -5. Now from that point, we've got to go and make 4 points going up, down, left, and right based on this r. So this is how we go up, down, left, and right from the center, about 2.5. I'm just going to call it 2.5 for the interest of my handwritten drawing. So if I start at 2 and I need to go right 2.5, I need to label up to 5. So 3, 4, 5. If I'm starting at a height of -5, I'm going to have to go down at least to -8. And if I'm starting at 2 and I got to go left 1, I probably need to label up to -1. Okay, so from the center, if I go right 2.5, from 2, that's 3, 4.5. So 4.5. Then I'll go left 2.5 from the 2. So 1, 0, -0.5. Then from the center, I'll go up and down 2.5. So starting at -5, that's -4, -3, -2.5. Back to the center, going down that much, -6, -7, -7.5. And it's a little elliptical on the left side, but that's all right. Connect with your nice, as best you can, circle. That's probably going to be the best circle you'll ever see me draw with a stablet. Again, the radius was not 7. I did not go left, right, up, and down 7. It was square root of 7. So I needed that approximation. Again, I would not do this on a no calculator test. So with these problems, we were given the radius in the center, asked to build the equations, which I did not box this one up. That was terrible. It's really weird not being able to look where you're writing. I know I've said it a million times, and I'll say it again. I want to highlight something before moving forward. When the center has a positive coordinate in the equation, it's a minus, because this is taking the opposite sign. It's x minus the value. But when that coordinate is a negative in the equation, it ends up becoming a plus. These are backward signs from each other. This is a theme we have seen before when we talked about horizontal shifts, and it's a theme that will continue as we move forward through this course. Very often we have one version of something being positive and then another version of the same thing being negative. It just depends on whether we're looking at data or an equation or a graph or whatever. So the signs in the equation are always going to be different from the signs in the center. That's an important aspect. All right. How are we on time? We got 10 minutes. Okay, that's plenty. Example 4. Let's go back to black. Let's identify the radius, the center, and then let's draw it. One more practice with drawing this. And for A, We're going to have x minus 3. And let's just draw A in the interest of time. If I think we have time to do B, we'll do it. But originally, I wasn't going to draw example 3s, but I did. So x minus 3 squared plus parentheses y plus 4 squared equals 9. Now remember, the format is supposed to be x minus h squared plus y minus k squared equals r squared. So our center, that's a coordinate pair, some a comma b. The x value is part of the x subtraction, the y value is part of the y subtraction or addition. So that says x minus 3. It's supposed to be x minus h. So because that's a minus, then a 3, that says the x coordinate of the center, the h, is 3. Conversely, because that's y plus 4, it's supposed to be minus. Well, y plus 4 is like having a minus a negative 4. So that's why the y, what am I doing? The y coordinate of k is supposed to be negative 4. Again, because that's a plus 4, that makes the coordinate negative 4. They are opposite in sign, just like this was a minus 3, so that's a positive 3. Then the radius, well, since this is a 9, that says that the radius squared is supposed to be 9. Taking the square root of both sides says that the radius is 3. I don't need a plus or minus because we're dealing with geometry. You can't have negative radii. So we have our center and we have our radius, and that is definitely enough to be able to draw this. So we're going to have a center at 3, negative 4. So another kind of bottom heavy one. Right 3. I'm going to go ahead and label up to 6. And then down 4, 1, 2, 3, 4, 5, 6, 7. I'm going to go ahead down to 7. Just labeling some of these. Okay, so at 3, negative 4, that's our center. I'll do that in red because it's not a point on the circle. It's just very helpful. And from that, we'll use the radius to go up, down, left, and right. 3. So from an x position of 3, going right 3 puts us at 6. Back to the center, from an x position of 3, going left 3 puts us at 0. Back to the center. From a height of negative 4, going up 3 puts us at a height of negative 1. Sorry that that's sitting on the label of 3. Back to the center, going down 3 puts us at a height of negative 4. Make a circle around all those. Boom, there we go. We'll have time to draw A and B. We'll do both. So for B, let's give you the equation x minus 3 squared plus y plus 4 in parentheses squared equal to 36. Hold on. I just did the same thing twice. X plus 5 squared, then plus y minus 1 squared equals 36. There we go. Sorry about that. So we can immediately tell everything. The center has to do with the 5 and the negative 1, but it's opposite in sign. So since that says plus 5, the center has to be at negative 5. Since it says minus 1, the center has to be a positive 1 for the x and the y coordinates, the h and the k. The right-hand side is the r squared. So r squared is 36. Take the square root of both sides, and that tells us that r is 6. No plus or minus needed once again. So our center is at left 5, up 1, with a radius of 6. So we need a left heavy graph this time. And that's a little slanted. There we go, a little better. So we got to go left 5, and then it'll be another 6. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And we'll also need positive 1 over here. So we're going left 5 and then up 1. So we'll need a height of 1. We'll also need a height of up to 1, 2, 3, 4, 5, 6, 7. And a height of negative 5. 1, 2, 3, 4, 5. You don't have to do all that at first. And again, not doing this by hand makes it a little easier because all that's already there for you. So negative 5, comma 1, there's our center. Left 5, up 1. From that point, we'll go left, right, up, and down based on the radius of 6. So going left 6 puts us at negative 1, negative 11, excuse me. I was looking at the 1. Going right 6 from negative 5 puts us at positive 1, back to the center. Going up 6 from a height of 1 puts us at a height of 7, back to the center. Going down 6 puts us at a height of negative 5 when we start at 1. So there's our plus sign looking thing, but we make our circle with that. And that's probably the worst one I've done, but you get the idea. And that will finish 2.8, which will finish the material for this chapter, which finishes the material for the test. So we finished it exactly on time, as I hoped. So that's great. So test 2 takes place next week. It's in my math lab. You're not going to see it yet. It'll go live on, like I said, Monday. Yes. But the review is available now. Where is the review? In Canvas. So it's a PDF that you can download. And it is right here. It has the questions, it has the answers, just like test 1, but nothing in between. You are responsible for using your notes, the lectures, your homework problems to fill in the in-between. The review will be very similar to the test. No curveballs, no big surprises. You know what my expectations are of you. Homework is due Thursday the 16th. Make sure you're getting that done as soon as possible. I don't think I have the due date set up in my math lab yet, but I will have that set up in the next day or 2. So that's it for the day. I don't want to spend the next 5 minutes going into chapter 3. We'll just go ahead and dive headfirst into that next class. So have a good one, get some work done, and we'll see you on the internet next time.